So here is the Mathcad for the design of anchors cast into concrete. In this case, it's an edge column, so we've got limited distance in one direction. So your base plate is relatively close to the edge of your concrete foundation. We start with the input. So what loads do we have? And I've taken this straight out of Multiframe and it's gone via Excel. Interestingly, if you cut and paste from Excel into Mathcad, it automatically creates a table. A table is just another way of presenting a matrix. So these values here are effectively a matrix. And you then populate the units and the variable value. And from that matrix, you can derive these arrays effectively. So we have strength reduction factors taken straight from the code. We take our design factored vertical load and our design factored horizontal load. So if you want the quick and dirty solution, you just take the worst shear with the worst tension. And if it works, you're good to go. But that can be quite conservative, and we'll see a bit later. So we derive what the maximum tension is in the bolt and what maximum shear is in the bolt by sharing it among the lot. And we've chosen 20mm anchors, and we're going to use grade 4.6. Now, as I've mentioned before, the steel strength is not usually the weakest link in the design of your base plate or your holding down bolts. And so it makes sense to use the lower grade 4.6 rather than the higher grade. Your higher grade is not giving you any more strength. The other aspect is with cast-in bolts, then they tend to get abused on site, and the grade 4.6 is more amenable to being reshaped and rebent. So we have a tensile strength of the anchor group. This is just the steel of 500 and a shear strength of 301 kilonewtons. So the steel isn't being pushed that hard, so our utilization is only 16% in tension and 27% in shear. Our combined utilization is less than 1.2, so we're good to go. Now the more complicated stuff and probably the weak link. Now I say it's the weak link. Now if you think about seismic design, you'd be preferring a ductile failure, and your concrete failures are not ductile. Your steel failures, particularly a tensile steel failure, is ductile. So let's check the concrete under tension. We have chosen a thickness of foundation of 300mm and a concrete strength of 30 MPa. Now, strength reduction factor comes from the code is 0.65, and we're putting a plate underneath the end of the bolt, under the head of the bolt, as 30 by 30 is a square plate. We're not eccentric, so we can go relatively simple in our design. We put in our bolt spacing and our edge spacing. So our spacing in one direction is 180mm, and in the other it's 230. For the edge distances, we've got 235 and 500 respectively. That gives us an edge distance, a minimum edge distance of 235, our C min, and then we do some magic with the ratios to come out with the formula. So if you look at the projected area of the bolt group, there is a formula given in clause 17.5.72 for the projected area of the bolt group, and we compare that with the projected area for a single bolt group. And we then derive our modification factors. So there's a whole load of modification factors given in the code from equation 17.8 onwards. So there's phi 1, which works out as 1, phi 2 works out as 0.994. Phi 3, now we're assuming cracked in service, so phi 3 is 1. We have a fiddle factor of K equal to 10 because there's a cast-in anchor, and a lambda of 1 because we're using null weight concrete. These will change if any of the assumptions change. From that, we can derive a basic concrete strength of 110 kilonewtons. If our embedment was greater than 280 millimeters, then we use the second value for the concrete basic strength, which gives us, if we add all those numbers together or multiply all those numbers together, we get a design breakout strength for the whole group as 144 kilonewtons. So our utilization is a little bit higher at 42%. Then we look at the tension pull-out strength of the anchors. We're assuming a bearing area under that plate. So remember, we assumed a 30 by 30 plate under the bolt head. Now, our spreadsheet uses the full area and just says it's the d squared, whereas I've always deducted the area of the bolt itself to be a little bit more conservative. Tell me which one you think is correct. Answers in the chat, please. But that gives you a pull-out strength of 216 and therefore a design pull-out of 140. So again, it's not particularly critical because it's a utilization of 11% in this case. Now we check on the blowout strength. Again, we're still in tension. And again, we've taken our bearing under the plate. And we have modification factors for our edge distances. Here, K1 works out as 0.782, which gives us a design blowout strength of 261 kilonewtons. Again, a relatively small utilization. So now we're looking at shear, and back to those diagrams given in the code. We work out what the shear failure area is. So pull down our applied loads. We've got a perpendicular load in shear of 47 and a parallel of 22. We're not eccentric and our K2 factor is 0.6. We've pulled down our edge distances and our spacing of our bolts, and a reminder of our C-min is 235. So we've chosen a 160 embedment bolt diameter. Now, there is a maximum load-bearing length of the anchor limited by the code as 8 diameters, which may mean you need a larger bolt than you would otherwise assume. This gives us a concrete breakout strength in shear of 80 kilonewtons. And then we have modification factors 5.5, 5.6, and 5.7. And again, we're assuming it's cracked in service, but we've got additional reinforcement. If you've got no reinforcement extra, then it goes to 1.4. This allows us to derive our projected failure area and the width of the shear face. BV works out as 935 millimeters. Again, we work out our projected failure area for the group and derive the concrete breakout strength for a single anchor perpendicular to the connection. In this case, our design capacity is 66 kilonewtons, whereas for parallel, it's 132 kilonewtons. Now we look at the concrete pry-out of the anchor in shear, and we derive a pry-out strength of 289. And that's well within the utilization requirement. So from all of the above, we can work out that our minimum strength of the anchors in tension is 140 kilonewtons, and our minimum strength in shear is 66. All good so far, but then we start combining. And if you combine the worst cases of tension and shear, you'll probably find your connection fails. So this is where I have split my results. So each of these rows represents a different load case. So you'll see our maximum shear doesn't occur with our maximum tension. So we've derived these arrays from our matrix, which was basically the table above, to give us our Rx, Ry, and Rz. And remember, multi-frame talks about linear forces in terms of Rx, Ry, and Rz. In our case, Ry is upwards, and for these load cases, everything's in tension, because when you were designing that anchor, we're really looking at the tension cases. So we can derive what the applied tension is and the applied shear by taking the vector sum and then doing a utilization check. Now it's over 1, but it's okay because it's below 1.2. Equation 17.5 allows you that margin. And here's a summary and a diagram to show you what's been going on. So that was the Mathcad for the design of the anchors.